Welcome to the webinar, An Evaluation of Thermally Stable PEEK as a Secondary Coating for Fiber Optics. I'm Jason Fant, Global Market Manager of Fiber Optics at Zeus, and joining me today is Matt Davis, a Lead Research Engineer with Luna Innovations. We want to thank you for attending as we look at the challenges of using PEEK as a secondary coating or type buffer, and our journey at Zeus to stabilize PEEK for its use as a coating. So why PEEK? At Zeus, we started looking at extruding PEEK as a fiber coating based on customer requests. Its strength to weight ratio, high surface temperature, impact, wear, and radiation resistance, as well as low outgassing, make PEEK interesting for sensing applications in the harsh environments found in energy, aerospace, and automotive markets. Some possible applications include protection for embedded sensors for structural monitoring and nuclear storage facilities, or composite parts for aerospace. Improved crush and abrasion resistance make it an attractive offering for downhole or subsea sensing. Other properties of PEEK, such as biocompatibility, excellent purity, and resistance to ETO, gamma, and autoclave sterilization, makes it ideal for the medical market as well. Protection from wear and the ability to handle repeat flexing make PEEK interesting for surgical robots, and the added strength can help with sensor deployment. When looking at PEEK as a coating for fiber, we find a material that can protect fiber, extend life, and reduce redeployments while still allowing strain, vibration, pressure, and other factors from the environment being sensed to transfer. Now let's look at some challenges with using PEEK as a coating for fiber. PEEK exhibits compressive strength and instability during temperature fluctuations, which can induce attenuation. What you see in this slide demonstrates that effect. As you see in the table, the attenuation improves as the temperature increases, reaching a 1.3 decibel per kilometer reading at 246 C. However, as the temperature drops, attenuation increases continuously, reaching a 15.6 decibel per kilometer at room temperature. When we cycle through the temperature a second time, the low attenuation is restored at elevated temperatures, but when cooled, we see the loss return to 15 decibels per kilometer. Additional issues can occur when dealing with fiber-containing gratings. For example, we found in distributed temperature gratings that when taking attenuation measures with our OTDR, the loss may be within the required loss bank of the cable, but compression could cause deformed DTG peaks that we weren't capable of seeing with our OTDR. Our goal at Zeus was to offer a PEEK coating that is stable during extreme temperature fluctuations, allowing the fiber to retain the benefits of PEEK without attenuation-inducing compression that we saw during the temperature cycles. After optimizing our coating process to stabilize the PEEK, our development team wanted to look at temperature effects at a micron level to ensure our coating caused no significant changes to the performance of the optical fiber. To analyze this, we compared a reference fiber with and without PEEK. Here you see the specifications for the fiber evaluated during the test. We used a radiation-resistant single-mode 125-155 polyimide fiber. The fiber was 410 meters continuous. For the PEEK sample, we added PEEK to the 155 polyimide from the same draw and lot as the control fiber for a final OD of 400 microns. The coil we tested was 455 meters continuous. In order to test our PEEK coating in a more in-depth way, we contacted Luna to perform the testing using their OBR 4600 or optical backscatter reflectometer. So I'd like to turn it over and ask Matt Davis from Luna to explain how the OBR tested the fiber.
Thanks, Jason. Luna's OBR 4600 is the industry's first zero-dead zone, ultra-high resolution reflectometry device with backscatter level sensitivity for interrogating optical components or systems. The OBR uses swept wavelength coherent interferometry to measure minute reflections in an optical system as a function of its length. The technique measures the full scalar response of a device, including both the phase and amplitude. Data is then presented graphically, providing the user with an unprecedented inspection and diagnostic capability for their component or network. The data may be used to locate loss events due to bends, crimps, or bad splices, look inside of a device using the micron resolution and sensitivity that interrogates the individual components within a subsystem, repeatedly measure and store the backscatter signal, which enables quality control and provides a record of what the cable looked like when it was manufactured, when it leaves a facility, and after it's been installed. The data may be used to locate loss events due to bends, crimps, or bad splices in a network. Look inside of a single device using the micron resolution and sensitivity to interrogate these individual components within a subsystem to determine some of their optical properties. Provide the frequency of each individual grating written into a fiber and determine their quality and their specific wavelength. Repeatedly measure and store the backscatter signal in a cable, enabling quality control and a record of what the cable looked like when it was received, when it's been processed, and once it's left the facility and is installed. And also to measure the signature and location of macro bends, which can be critical once a cable has been installed to determine loss points. The backscatter signal can also be used to measure strain or temperature within the cable or on a device. When data is taken, the amplitude in the time domain is equivalent to a traditional optical time domain reflectometer or an OTDR measurement. However, the optical frequency domain reflectometry, or OFDR method, in which the data is collected in the frequency domain and processed through a series of algorithms that transform the optical signal to provide both polarization and amplitude information on the device or network. Operating in the frequency domain is what enables the no dead zone micron level resolution measurements within a network or component. An example of a scan from an optical network is shown. In this network, it's easy to identify the quality of the connections, the location of a bad splice, and to see inside of a device like a coupler or a single grating that's been written onto the fiber. Some of the key specifications for the OBR 4600 include less than 0.05 dB of insertion loss resolution, a tenth of a dB in accuracy, a 70 dB dynamic range, and a measurement range of up to 2 kilometers. The test was configured as such that the OBR was attached to a 150 meter delay line, which acted as a jumper between our two samples and the test location. The two fibers were coiled in approximately a half meter diameter loop and placed into the freezer and the furnace for the thermal cycling. In each test, K-type thermocouples were used to record the temperature of the environment the fiber was placed in. At each temperature interval, both of the fibers were scanned and the data was saved for later processing. These data were evaluated by using the OBR software to measure the loss within the fiber along a 250 meter section of each, beginning 50 meters from the end of the delay line. This data was processed to determine the attenuation within that section of the fiber to demonstrate whether or not the peak coating had any effect on the fiber. To record the data from the K-type thermocouples, an Agilent 34970A data acquisition system with a multiplexing acquisition card was used, and then the temperature of the fiber was changed by placing it in a sub-zero freezer and also a high-temperature furnace, which were located at Zeus's facility. Prior to beginning this test, we took a baseline scan with the OBR for each of the fibers. This data is shown here on the plot. The loss event seen at the 150 meter distance for the peak-coated sample was due to the connector loss between the 150 meter jumper and the beginning of the peak fiber sample. You can see that the reference fiber averaged a 1.2 dB per kilometer attenuation, and the peak fiber was equivalent with about a 1.23 dB per kilometer. One of the advantages to using the OBR to make this measurement is the ability to measure the polarization states of the fiber. In this case, we measured the polarization state of the peak-coated fiber and also the reference fiber and compared them. The evolution of the OBR receiver polarization states as a function of the fiber length appear to be what one would expect from a coiled section of fiber, where the S&P states from the fringes, with a period on the order of a few meters, is consistent with the birefringent's beat length induced by coiling the fiber. There did not appear to be any inconsistencies in viewing the differences between the reference or the peak, suggesting that minimal, if any, residual strain has been induced by the coating process that would affect the optical properties. The first series of tests that was performed involved placing both coils of fiber onto a sheet and into a sub-zero freezer and allowing the temperature as measured by the thermocouples to stabilize. This was repeated multiple times, and measurements at the stable temperatures were taken using the OBR. The table shown summarizes the results that we got. As you can see, the average loss for both fibers, or the attenuation, is effectively the same, demonstrating that the peak coating did not affect or present any major changes versus the reference fiber. Again, K-type thermocouples were located within the furnace to provide a measure of the temperature near where the fiber was within the furnace. The thermocouples did identify that there was a gradient that existed, which was typically on the order of 10 degrees C or less. The data was analyzed using the same methods as it had been for the sub-zero test. In reviewing the data, it was observed that both the reference and the peak-coated fiber averaged an attenuation on the order of 1.5 dB per kilometer at each temperature point. And both of the fibers demonstrated very similar characteristics up to approximately 150 degrees near the glass transition point of the peak material. Above 150 degrees, it appeared that the peak experienced a little bit less attenuation. However, as you can see, looking at the data as a whole, there's effectively no significant effect induced into the optical performance of the fiber by the peak coating. In this plot, the data from the previous slide is shown graphically. Again, you can see that the reference fiber demonstrated a slight increase in its attenuation with respect to temperature, which would be expected. And the fiber that had been coated with a peak, its attenuation decreased slightly. However, being that these are so similar, it reinforces our conclusion. After the fiber was cycled in the freezer in the furnace, a test was conducted to quantify the loss that could be attributed to inducing a bend of a known radius into the samples. For this test, a fixture was designed to hold the fiber at 3 different radii of 50, 30, and 10 millimeters respectively. An image of that fixture can be seen in the bottom right of this slide. On the fixture, the fiber was clamped on one side using a spring-loaded clamp that had a small silicon pad. The pad prevented the fiber from being strained or broken by the force of the clamp. The fiber was wrapped 1.5 times around each mandrel, and scans were taken. For each test, the locations of the spring clamps were determined by artificially inducing an attenuation into the fiber while a measurement with the OBR was taken. This location was then recorded, and the data in between the spring clamps could be analyzed. For each radius, a scan was taken at ambient temperatures and then also at an elevated temperature near 140 to 150 degrees C. The data was analyzed in a similar fashion to the previous tests. The measurement points were spaced 30 meters apart on the fiber, centered around the location of the bend. The reference fiber was not expected to show any change in its attenuation when returning to ambient conditions during the thermal cycling, and this was verified for the 5 and 10 millimeter sizes. For this reason, a measurement at 30 millimeters was not taken. The most significant finding was for the 10 millimeter radius, in which the peak-coated fiber exhibited less loss than the reference by a significant amount. This is most likely explained in the thickness that has been added to the fiber as a result of the peak coating. This would place the light guiding core of the fiber at a larger radius than the uncoated fiber by a very small amount. Even this minimal change could account for the smaller amount of attenuation that was measured. This concludes the discussion of our test results. At this point, I'm going to pass it back over to Jason.
All right, thank you, Matt. Now let's look at some conclusions. Using a measurement of backscatter pattern in the fiber, testing demonstrated that there was no significant loss or stress concentrations introduced into the fiber as a result of the coating. The average variation of the peak-coated fiber's attenuation during temperature cycling is within 0.02 decibels of the control fiber. This shows the stability of the peak is not significantly affected by temperature cycling or thermal shock. It was also observed that the peak-coated fiber showed significantly less loss at the tightest bend radius over the control fiber. All right, that concludes our presentation. I want to thank everyone for attending, and we're now ready for Q&A.
Okay, Jason and Matt, thank you very much for that great presentation. Now, we do have some questions that have come in from our attendees, but before we get to them, I'd like to remind everyone, if we don't get to your question, don't worry. We'll have an answer for you following the webinar. The complete Q&A transcript, including the answers we don't have time for, will be sent to all of our registered attendees and will be posted with the webinar when it goes into the on-demand mode. Okay, now it's on to the questions. Gentlemen, your first question asks, can you explain how you changed your process to stabilize the peak?
Well, we're unable to discuss specific processing information because we're going to consider that proprietary. We employ a solution-based approach. We develop a process and a product that addresses an unmet need. So we'll share the capability improvements as they relate to the end product's characteristics, but specific processing parameters, we're going to consider that proprietary as intellectual property.
Thank you very much for that answer. Here's another question. What is required of the optic to put peak on it?
The primary coating of the fiber must be able to withstand our proprietary process. We can largely determine feasibility by reviewing the fiber data sheet and confirm processability with a short validation run. This can also be influenced by the required properties of the final product.
Okay, great answer. Let's take a look at another question, shall we? How long of a continuous length can you produce?
We have run lengths well over 1 kilometer. However, the quality of the fiber, the specification of the final product, as well as many other attributes can go into determining how long the length we can actually achieve. So this will be something that, again, we would have to determine on a case-by-case basis.
Okay, and thank you very much for that answer. Here's another question. Can you hand strip the peak for splicing?
Peak cannot be easily stripped by hand. It can be thermally or chemically stripped effectively. There are some commercial strippers capable of stripping peak, but you should consult the manufacturer on how this affects the number of uses between cleaning and other parameters involved in the use.
And thank you very much for that answer. Let's take a look at the next question from one of our attendees. Does the thickness of the coating affect the performance of the fiber optic?
In our experience, we have not seen a correlation between the thickness and the performance of the actual fiber optic itself.
Thank you very much for that answer. Let's take a look at another question. Why doesn't the OBR have a dead zone?
The OBR is a frequency domain reflectometer. It sweeps a tunable laser and makes the measurement based in the frequency domain versus the time domain, compared to an OTDR that has a specific pulse width that is tied to the distance range, which will blind the receiver based on a reflection located within the network, typically the front panel connector or somewhere along a launch reel. The OBR does not have to deal with this as it operates truly in the frequency domain and does not have to deal with the reflections from a pulse like an OTDR.
And our next attendee asks, how is the OFDR system so accurate?
The accuracy is tied to the fidelity of the tunable laser that we use to sweep the wavelengths making our measurements. The laser is calibrated on every sweep to a NIST-certified internal gas cell for wavelength alignment. This is what allows the OBR to provide the highest resolution of a commercially available reflectometer on the market today.
Okay, thank you very much for that answer. It looks like we have another question from one of our attendees. Do you have samples available to test?
Yes, you can contact us at zeusinc.com and someone will respond with sample availability and the possibility of setting up a validation run.
Okay, gentlemen, thanks for that last answer, and it seems we're almost out of time, so we're going to have to wrap up this webinar right there. Jason Fant and Matt Davis, thank you very much for spending some time with all of us today. And we'd like to say a special thank you to all of our audience members for being part of this webinar event. Take care, and we'll talk to you soon.